Welcome to the fascinating world of neuroscience. Today, we are going to explore how neurons communicate with each other to make decisions. We will dive into excitatory and inhibitory postsynaptic potentials, commonly known as EPSPs and IPSPs. These tiny electrical signals are the fundamental building blocks of all brain activity, from moving a muscle to forming a complex memory. Let us begin our journey into the microscopic world of the brain. To understand how neurons activate, imagine you are sitting in a car. Pressing the gas pedal gives the car a burst of energy to move forward. In the brain, an excitatory postsynaptic potential, or EPSP, acts exactly like that gas pedal. When excitatory neurotransmitters like glutamate bind to a receiving neuron, they open specific ion channels. This allows positively charged sodium ions to rush into the cell. This influx of positive charge makes the inside of the cell less negative, a process called depolarization. This electrical nudge pushes the neuron closer to the threshold required to fire its own signal, known as an action potential. Without these excitatory signals, our nervous system would be completely paralyzed. Now that we understand what an EPSP is conceptually, let us look at how we can calculate its exact size. This formula is essentially a modified version of Ohm's law applied to a biological membrane. The symbol delta V represents the change in the membrane voltage, which is the actual size of the EPSP, measured in volts. I sin stands for the synaptic current, representing the flow of positive ions entering the cell in amperes. Finally, Rm is the membrane resistance in ohms, which dictates how easily ions can leak back out. Physically, if the synaptic current increases because more neurotransmitters are released, the resulting voltage change will also increase, creating a much larger and more powerful EPSP. Before we move on, let us see this formula in action with a concrete example. Imagine a laboratory experiment where we measure a single neuron. We are given a membrane resistance of 50 megaohms and a tiny inward synaptic current of 0.1 nanoamps. We need to calculate the resulting change in membrane voltage. We chose our modified Ohm's law formula because it directly relates these exact electrical properties. By plugging in our values and multiplying the current by the resistance, we calculate a raw voltage change. We then convert this result into millivolts, which is the standard unit in neuroscience. The final answer is 5 millivolts. Physically, this means the inside of the neuron just became 5 millivolts more positive, taking a meaningful step toward firing. Building on that calculation, let us look at a more realistic scenario involving the firing threshold. A neuron is resting at negative 70 millivolts, and it needs to reach negative 55 millivolts to fire an action potential. If each EPSP adds exactly 3 millivolts of positive charge, we want to know how many simultaneous EPSPs are required to trigger the neuron. First, we find the total voltage gap by subtracting the resting potential from the threshold, which gives us a required shift of 15 millivolts. Next, we divide this 15 millivolt gap by the 3 millivolt size of a single EPSP. The final answer is 5. This shows us that a single synapse is rarely enough. It requires the teamwork of exactly 5 simultaneous EPSPs to push this neuron over the edge into firing. Having seen how neurons are excited, we must now ask how they are controlled. If EPSPs are the gas pedal of the brain, inhibitory postsynaptic potentials, or IPSPs, are the brakes. When a neuron receives a stop signal from neurotransmitters like GABA, specific channels open to allow negatively charged chloride ions to flow into the cell. This addition of negative charge makes the inside of the cell even more negative than its resting state, a process called hyperpolarization. This actively pushes the membrane potential further away from the firing threshold. IPSPs are absolutely critical for maintaining balance. Without them, the brain would suffer from runaway electrical activity, leading to conditions like epileptic seizures. They ensure our brain activity remains precise and safe. Now that we know how IPSPs act as brakes, let us examine the math behind this inhibitory flow. This formula calculates the synaptic current for an inhibitory synapse. Conceptually, it states that the flow of ions depends on how many doors are open and how hard the ions are being pushed through those doors. I syn is the synaptic current. The symbol G syn is the synaptic conductance, representing how many ion channels are open. Vm is the current membrane potential, and E-rev is the reversal potential for the specific ion, like chloride. The difference between Vm and E-rev is the driving force. If the membrane potential becomes less negative than the chloride reversal potential, the driving force increases, causing more negative chloride ions to rush in and hyperpolarize the cell. Let us apply this concept to determine the driving force acting on chloride ions during an inhibitory event. We are given a neuron with a resting membrane potential of negative 65 millivolts and a chloride reversal potential of negative 75 millivolts. We need to calculate the driving force to understand which way the ions will flow. We use the driving force portion of our synaptic current equation, which is simply the membrane potential minus the reversal potential. By substituting our given values, we subtract negative 75 from negative 65. The double negative becomes a positive, resulting in a final answer of positive 10 millivolts. Physically, because the driving force is positive and chloride is negatively charged, there is a strong inward pressure pushing negative ions into the cell, making it harder for the neuron to fire. We have now explored both the gas pedals and the brakes of the neuron. But how does the cell make a final decision? Imagine the neuron is a judge, and the synapses are people voting yes or no. A single vote is rarely enough. The neuron must act as a biological calculator through a process called synaptic integration. This happens in two main ways. Spatial summation is the adding together of signals generated simultaneously at many different synapses spread across the dendrites. Temporal summation is the adding together of consecutive signals generated at the exact same synapse in rapid succession. This integration is the very basis of neural computation and decision-making, allowing a single neuron to process complex, conflicting information from thousands of sources. To see exactly how this biological calculator works, we use the synaptic integration formula. Conceptually, this equation simply tallies up all the competing electrical votes. V-net represents the final, total membrane potential of the neuron after all inputs are considered. V-rest is the baseline resting potential of the cell before any signals arrive. The first sigma term represents the mathematical sum of all the positive voltage changes caused by excitatory inputs. The second sigma term represents the sum of all the negative voltage changes caused by inhibitory inputs. Physically, if the positive nudges overpower the negative nudges and V-net ends up higher than the threshold voltage, the neuron will successfully fire an action potential. Let us put this integration formula to the test with a complex scenario. A neuron rests at -70 millivolts with a threshold of -55 millivolts. It simultaneously receives 3 EPSPs, adding 4 millivolts each, and 2 IPSPs, subtracting 3 millivolts each. We need to find the net membrane potential to see if it fires. We use our integration formula to sum all electrical inputs. First, we calculate the total excitatory input, which is positive 12 millivolts. Next, we calculate the total inhibitory input, which is -6 millivolts. We combine these with the resting potential. The final answer is -64 millivolts. Physically, because -64 is still below the -55 millivolt threshold, the neuron will not fire. The inhibitory signals effectively canceled out the excitatory ones. To truly visualize this microscopic battle, let us look at a graph of synaptic integration over time. On the horizontal axis, we have time in milliseconds, and on the vertical axis, we have the membrane potential in millivolts. Notice the dashed line at the bottom, representing the resting potential at -70 millivolts, and the upper dashed line representing the firing threshold at -55 millivolts. You can see a small bump upward representing a single EPSP, followed by a dip downward representing an IPSP. Further along, multiple signals arrive close together, demonstrating spatial and temporal summation. The curve sharply rises, crossing the threshold line, which triggers the massive spike of the action potential. This diagram beautifully captures how the neuron weighs opposing forces before finally passing the message along. We have covered a tremendous amount of ground today, so let us review the most important ideas. First, excitatory postsynaptic potentials, or EPSPs, push the neuron toward firing by letting positive ions in. They are the gas pedals of the brain. Second, inhibitory postsynaptic potentials, or IPSPs, pull the neuron away from firing by letting negative ions in. They act as the essential brakes, preventing overexcitation. Finally, a neuron constantly weighs these opposing signals through synaptic integration, acting as a microscopic calculator. Only when the excitatory inputs sufficiently overpower the inhibitory inputs will the neuron cross its threshold and fire. You now have a solid understanding of the fundamental forces that govern all neuronal communication. Excellent work.